Okay, today we're going to talk about compound interest and exponential growth. So there's a couple of formulas that we're going to go over just to get started. So the first one is one that we actually talked about before, and this is the simple interest formula. And it looked like this, if you remember, we said the balance is equal to the principal times 1 plus the rate to the t. So this was our time, and usually time is in years. Sometimes they can have it in other things depending on what you write the equation in terms of. If you remember, this was our rate, and of course it always has to be in decimal form. This is the one that this one is actually just to get back original amount, if you remember. So when you multiply the principal by the 1, and then you multiply the principal by the rate, it gives you the principal, which would say if you had $100 in the bank, it would say 100 plus 100 times the rate. So this would add the interest to the original 100 that you had, and so it will give you the amount in the bank instead of just the interest rate, if you remember. And we said that this one was the balance, and this one was the principal. Okay, so that was our simple one. We're going to look at that one today just a little bit. The one that we're actually going to look at is our compound. Now this one we said is a little bit closer to what actually happens. If you actually look at the formulas that they use, they're super complicated, a lot of them. So we use sort of a simplified version, but this is closer, I guess, to what you might actually use to find interest. So T is still for time, and R is still for rate, and this is still the principal, and this is still the balance. This new thing that we've added, which is both of these ends, right? Because if you use the same letter in the formula twice, then it has to be for the same thing. This N is for the number of times compounded. So compounded might be a new word for some of us, but if you've done any work with these exponential functions before, or if you've done anything maybe in, economics, or I don't know, some of your other classes, you may have heard this word compounded. So compounded means how many times they're going to actually give you interest over the course of the year. So this formula would be like if you put all your money in the bank and then on the very last day of the year, they gave you all your interest all at once. This one is a little closer because what it does is it breaks the interest up and gives you interest over the course of the year. So N would be the number of times they're actually going to put the interest into your bank account. So, or, like on your credit card, if it's the other way around, right? So if they gave you interest monthly, it would mean at the last day of the month, every month, they would put a little bit of interest into your account. And they would have to break that rate up. So if it's a yearly rate of 10%, and they were going to do it over the whole year, so they were going to put it in every month, they wouldn't want to give you 10% every month. They would want to give you 1/12 of that 10% every month. So N would break it up into the number of right pieces, but then you have to add the interest more often, right? You're adding it more often, so you have to do this formula over and over again. So it's not just going to be the number of times a year that you're multiplying, but also the number of months that you're putting it in, or the number of times you're compounding it. So this finds the balance after every time you put interest into the account. This one works because if you're only doing it once a year, then this would be T. You're only putting interest in every year. You only need to do it T number of times. But if this one puts interest in every time that you put interest, so if it's daily, it's 365 times, but it breaks the rate up into that many pieces too, so that you're not putting a big 10% into there every day. You're only putting 101 over 3 or 10 over 365. So this breaks it into the right number of pieces. Now the other one that we're going to be using today, and I think we'll do on another video, where this comes from. So If you want to look at the other one, you can. It's going to be on E, continuously compounded. So I'll put up a video on E and a little bit more about that, and base E and the natural log and all that stuff. That will be on a separate one. But just for a compounded interest, because otherwise these videos get way too long. So the balance is equal to P E to the RT. And again, if you know a little bit about E, he's just a number like pi. So he's just an irrational number. He's a constant. He's about 2.7 something. So E is just this number that we use. He's in calculus, you'll find out where he comes from. He's a special number. He doesn't just come up randomly. Just like pi is he comes from somewhere. He's just not this made up number. But 2.7 is about his approximation. And again, this one's going to be the rate, and this one's going to be the time. And what does it mean to compound continuously? Well, this one's even closer to what actually happens, because continuously compounded means that we're adding interest basically every second, every nanosecond, every whatever smaller than a nanosecond, right? All the time they're adding interest. And E kind of models that number. If we could imagine that we were putting interest every second, an infinite number of times we're putting interest into your account or onto your credit card bill, E would model this number. And again, if you want to see why, I'll put up another video on that later, okay? So these are the three formulas that we're going to be using. This one we're going to use probably not as much. These two we're going to use a lot. This one we're going to use especially for things like exponential decay or population growth or those kinds of things that happen all the time. And these ones will be more about like bank interest or different things like that are kind of more artificial. But things that are happening constantly, this is usually the formula we're going to use, okay? So you want to have those little three formulas with you. They are in the textbook. You can look them up. They are probably under these titles, and you can get a hold of them. So what we're going to do is we're going to do an example of these things. And I just had the paper here. So let's see if I can get back. And we're going to use all three of those formulas just for practice, okay? So the first example, we're going to use the simple interest one. So we just made up this little person, Ivy. Her parents are going to send her to college, like hopefully all of you guys are going to be going to college. And they're starting to think about how are they going to pay for that? Because, of course, college, as you know, is pretty expensive. So Ivy's parents have $2,500, and they put it into an account that receives 3.5% interest. So I don't know where they found a bank that gave you 3.5% interest, but let's pretend that exists in real life. And then she says she'll start college in 9 years. Oh, and I don't know why I put a question mark, because that's just a statement. So we'll say period. Okay? All right. The first one says, using simple interest, just the compounded yearly, how much will she have in 9 years if this is the situation that she's in, right? So what is our simple interest? This one is the balance is equal to the principal plus 1 times the rate times t. So all I'm going to do is plug in what I know. So what do we know? We know the years, right? So this one would be time. What else do we know? We know, let me get some other colors out. We know the rate. So here's our rate right here. And we know the initial amount, so the principal, right? So that's how much she's going to be depositing in the bank. And we know that the rate is 3.5, but we know that we have to convert that to a decimal. So how do we convert percents to a decimal? So if we have 3.5%, we want to move the decimal point 2 places this way. So we're going to have a 0, 3, 5. So this will be my rate. Okay, so it'll be a 0.035 when we use it in our equation. Because, of course, whenever you're using percents in an equation, you need to convert them to a decimal. Okay? So here goes my balance. My balance is equal to my principal, which we said was 2500. It'll be 1 plus 0.3035. And you can write that as 1.035 if you like, of course, because that's the same thing. And the amount of years that we're going to have it is 9. Okay? So again, I'm going to be typing this into a calculator, so I'm just going to write it like this. So if you don't have your calculator with you, try to grab that now. Or if you don't have it turned on, turn it on now. Okay, so here's my calculator. And this is the thing I'm going to try to type in. So I'm going to just type in my 2500. I'm going to open my parentheses, and the parentheses are right here above your numbers, right above your numbers. You see them? And I'm going to put 1.035. And to raise it to a 9, of course, I'm going to use this little guy here. He's hard to see because the sun's glaring on him here. That's the little caret. Can I move? Do you see him? So there's my caret. And I'm going to put it to the 9th power and hit enter. So in 9 years, 9 years have passed. And how much does she have in the bank? Well, 3407.24, and I'm going to round it to 2 decimal places since it's money, and most of us, don't carry around tenths of a cent, so I'm just going to round it to the nearest penny. Okay, so let's look at some of these other ones. So number 2 talks about this other formula where we're going to be compounding it a certain number of times. So the first one says compounded quarterly. So we're going to work on this one right now. So quarterly. So what does quarterly sound like to you? Hopefully when people hear quarterly, you're thinking of 1 quarter. So 1 quarter of the year, that means we're going to be doing it 4 times a year. So this would be 4 times a year. Or in other words, every 3 months, right? 4 times a year. All right, now the formula we're going to use here is going to be the balance is equal to the principal. We always have to add the principal back in, so we have to keep that 1. But we're going to divide the rate up into pieces this time. We're going to divide it up into 4 pieces. So I don't want to give 3.5% every quarter. I only want to give a quarter of that, I guess, right? So I'm going to break it up into 4 pieces. But now I'm adding the interest 4 times as many times. Okay, so when I put this formula together, of course, the numbers are basically the same. My balance is going to be equal to, well, I'm still depositing the same amount of money. This is still going to be a 1. My rate is still going to be the 0.035, but I'm going to divide that by 4 this time because I'm going to break it up into 4 pieces and give it to Ivy every 3 months or 4 times a year. And I'm going to do it 4 times in each year. And how many years am I going to be doing that? 9 years. So do you see how I use this formula? Okay, so once again, I can simplify this up if I want to type it into my calculator, or I can try to type it in as is. I think a lot of people sometimes make a mistake when you're trying to type it in as is because this one would probably require some extra parentheses. So my suggestion to you is simplify it a little bit unless you are very savvy with the calculator, and a lot of you are kind of still novices with the calculator. So what I'm going to do is I'm actually going to figure out this thing inside first. And how I'm going to do that is I'm going to do the 0.035 divided by 4. And that way I didn't need to use any parentheses for that part. And then I'm going to add 1 to it. Now the trouble with doing it this way is you can lose accuracy, because if this doesn't come out to be a nice number that has a relatively small number of decimal places, you can actually lose a lot of the accuracy. So what I'm going to do here is I'm going to hit this button down here that says STO, and this stands for store. And I'm going to hit store. And you see what happens here? You get answer with a little arrow. And what I'm going to do is I'm going to store this answer in my calculator under a letter. I'll just call it, alpha A, only because, so I hit alpha and I hit this one. So you do see the little green A above? And if I hit the alpha, it'll make these letters. And so what I did was I stored it as A. And now every time, so here, look, clear this out. Every time I hit the letter A, until I change it to something else, it's going to come out to be this. Now I can store on top of A and use it again. As soon as I store another number, it'll be that number instead. But for right now, every time I type A, that's the number that will come out. So what I'm really going to type into my calculator is this. And of course, to the, well, what's 9 times 4? 36, right? So that's what I'm actually going to type into my calculator because I've already named this A. All right, so it's made my life a little bit easier instead of having to worry about getting all those fractions typed in. And it only took me a second. So here's my caret and my 36. And this time, it should come out pretty similar to what we had before, but actually a little bit more. And hopefully, I'm going to round it to 96, because that's to the nearest penny. Why is it a little bit more? Well, every time they add interest, we get interest on that interest. So the first one, we were only getting interest at the end of the year. So this one, we got interest. They added the interest at the end of the year just once. So I didn't get any interest on my interest, except at the end of the year. So, we had to wait a whole year to start earning interest on our interest. This one, I only had to wait 3 months to start earning interest on my interest. So I was gaining money faster in this one. Okay, so each one of these should give me a slightly different answer. So if I compound it monthly, I actually should be getting a little bit more than this one because now I only have to wait till the end of the months to start earning interest. And this one, I'll only have to wait to the end of the first week. And this one, I never have to wait. I'm going to be earning interest the whole time. So you ready? Let's just do the last couple of ones quickly here so that we can see how they come out. But hopefully you kind of get the idea here after looking at this first one. We're basically plugging this information into my formulas, and I'm just putting in the right amount. So this one was my quarterly. Let's do my monthly. So what's going to change? Not a whole lot. Everything else stays the same, except this number. Instead of 4, if we're doing it monthly, we're going to change it to a 12 because there's 12 months in the year. So now we're going to be adding interest not 9 times, but 12 times 9 times. And again, we can put these numbers into our calculator and store them. So you know what I'm going to do is I'm going to do this one and this one. You ready? If you know what 9 times 12 is, you're okay, but I'm going to just do it just so you can see that we can store lots of numbers in here. So I'm going to do 0.035 divided by 12 plus my 1. So that's the thing inside the parentheses. I'm going to just go ahead and hit my store button. And I'm going to save that as A again because I don't need that number from the last question anymore. So I'm just storing this one as A. So I'm calling this whole thing A. Then I'm going to do 12 times 9, and I'm going to store that, so I hit my store button again, as B. So this one is the B. So here's B. So what am I going to type into my calculator now? Now all I have to type in is this, 2,500 A to the B, because I stored those numbers as letters. So 2500 alpha A, and of course when they're scrunched up next to each other, it means to multiply anyway. I have to put the caret to raise it to the power, and B. So this one came out slightly more, 3.424.07. Okay, cool, right? Let's just do the last two on this one, and then we have one more to look at. I'm trying to go fast because I know after a while looking at these videos, it probably gets slightly tedious. So let's do weekly, and then so that'll be 2500, 1 plus. Can you guess what I'm going to put for my denominator this time? Yeah, 52. Why did I choose 52? Hopefully everybody knows. Why? Because there's 52 weeks in the year. So with these math problems, you need to bring a little bit of your own information, but mostly it's fine. Mostly it's stuff that's actually already in the question. This time I put the fraction second. Do you see that? And so I had to put parentheses so that it would do, well, actually, I guess it would do the division first anyway, because it's going to follow the order of operations. But I put the parentheses just to make sure it did, because I feel like that makes me feel better if I do. All right, so I'm going to store that one as A again. I'm going to do 9 times 52. And I'm going to store that, because again, if I don't multiply those together, I'm going to need to probably do parentheses in my next equation. So again, I called it A and B, so it's going to be 2500 alpha A raised to the B. Ta-da! 3425. So that one wasn't a whole lot more. I'd like $1 more. You didn't get a ton more. But all right, last one is compounded continuously. Now, compounded continuously is the one we want to use our new formula for. So this formula, if you remember, is the balance is equal to P e to the RT. So E is a constant. He's just a number. I'm not going to put anything in for E. E is like pi. E is like, those like square root of 2. It's just a number. It's not a number that we love because he's irrational. And as people, we don't really like those irrational numbers. But so 2500, E stays where he is because he's a constant. My rate is the same. And the amount of time this time is going to be 9. Okay. So how do I type this into my calculator? Well, fortunately, my calculator knows that I have to use E all the time. So I'm going to clear this out so it's easier to see. I'm going to do my 2500, and then I'm going to go down here, and do you see this one says E to the X like above? It's a little bit hard to see, but above this ln, I'm going to hit my blue button this time, my second button, and I'm going to hit this one. And you see how I put the E with the caret already for me? And what am I going to raise it to? I'm going to raise it to 0.035 times 9, and I'll just close those parentheses. This one should come out a little bit more than the others. Not a whole lot more, but there it is. 342564. Now, or 65, I guess. As we start to, if this were a bigger amount of money or a longer number of years, that amount in which they are different would start to be a lot more. You would notice it would start to get bigger and bigger and bigger. But that's what it is now. Okay, now the last question here is a little bit different. It says, when will her money quadruple? So let's just fold this over so we can use this question again. But we can start with a clean sheet kind of here. Okay, so it says, when will it quadruple? What does quadruple mean? It means be 4 times as big. Okay, so let's talk about let's use our our continuously compounded formula. We want to know when it will quadruple. So the original one was $2,500 that she put in. So if I want to know when it's going to be 4 times as big, well, how will we find out how much money that is? We multiply 2,500 by 4, right? And that's going to give us this amount, $10,000, right? E, we know the rate is 0.035, but we don't know how long it's going to take to get to there. We know it's a lot more than 9 years because 9 years only gave us like $3,500 or whatever. Okay, so the first thing we're going to do is we're going to divide both sides by this 2,500, and what you're going to notice is something funny. Hopefully you'll see it too. What does this come out to be? 4, right? So when we're talking about these ones where it says quadruple or get 3 times as big or get twice as big, it doesn't matter what amount we start with, because remember, these are percentages bigger. So if it's going to quadruple, this number is always going to be a 4. It doesn't matter what the balance is in this is, because you're always putting a number over here that's 4 times as big as this one. If I started with $1, you would have put 4 over here, and when you divided, you would have had a 4, right? So it doesn't matter what the principle is. If it's going to quadruple, you're always going to end up with an equation where it's e to the RT is equal to 4. If it's 3 times as big, it's always going to be e to the RT with a 3 over there, because you're putting a number 3 times as big or 2 times as big or whatever they want there, right? So if they don't tell you the initial amount, which they don't sometimes, they say just how long will it take to triple or double, use a 1 and a 2, twice as big, or 1 and 3 if it's going to be triple, 1 and 17, or how long does it take to get 17 times as big. Okay? All right, so here, now we want to solve this, but if you remember, the thing we're trying to solve for, I didn't put my 3.5. Why didn't I put my 0.35? The thing we're trying to solve for is up here in my exponent. So this is where I'm going to have to log both sides. Now I'm going to use the natural log. So that was that ln thing. And why did I use natural log? Because natural log means log base e. So this says how long does it take, or what number do I need to raise e2 to get e to the 0.035t? So what do I need to raise e2 to get e to the 0.035t? It's just this, right? That's how big that number is. So this one's just going to be 0.035t. This one is ln 4, which I don't know what that number is, but the calculator can help me with that later. So I'm just going to leave that alone for now. Whenever I get it down to a log without an exponent, without a variable in it, I know I'm just going to leave it alone and work with it that way instead of converting it to a decimal. Because not only is it smaller to write on my paper, but also it keeps it more accurate if I don't change it to a decimal to the end. Okay, so now I know what t is. It's this number. And again, if you had left it like that, I actually probably would be okay with it. I'm okay with that. But we want to know the time. So if you told me the number of years was ln 4 over 0.035, I'd probably be very upset with you as a normal human being, right? Because that's annoying for you to say to me. So since I want to actually know how many years it is, I'm going to figure it out. But if I were going to use this in a formula or something later, I wouldn't convert it. But since I do need to know what it is, I'm going to do it. So I'm hitting that ln button, the one that's underneath the e to the x, because these guys are actually inverse functions, so they put them on the same key. Isn't that convenient? Divided by 0.035, and it tells me it's going to take me about 39 years. Well, closer to 40 years, right? 39.6 years to actually get $10,000 in my account. So I'll be an extra old lady. You people will probably be feeling like you're old people by then too. All right. So that was a quick run through of how to do your compound interest questions. I'll put up some more videos with some more examples. But do your best, see what you can come up with, and see if you can figure them out. Read over your textbook, look at some examples on your other resources, and see what you can do.